My name is Xinwu Qian, and I'm from Purdue University. So today I'm going to present a topic on forecasting short-term taxi demand using boosting-GCRF. So basically, this kind of problem is transferable as with what is presented from last speaker. Just replace taxi demand with speed and replace zone with a link. It's pretty much the same. But I will discuss about what are the challenges remains in this problem and what is the methods that we're using to address all of these challenges in this problem. I hope you'll find this interesting. So this is a collaborative work with Professor Kusuri at Purdue University and Professor Chao Yang from Tongji University. So today's presentation, there are 5 sections. We'll start with a brief introduction and motivation, followed by several challenges, which motivates the use of our methodology. And then we present the numerical experiments. It's quite comprehensive. And finally, we present the conclusion and some future works. So to begin with, I assume most of you are really familiar with taxis. And think of taxi industry back in 5 years ago, when there's no Uber, when there's no app-based services. What happened is like taxi is the only choice we have if we want to move from like door-to-door travel, besides self-driving, especially in urban areas. It's because it's a monopolistic market. Taxi, there's no competitions. There's just TOC doing the regulation. And the most popular methods back to 5 years ago probably is like street hailing. That's straightforward. We just wait on the curbside and wave our hands for a taxi. And how large is the size? So just take New York City as an example. That is the data from 2016. We have over 16,000 registered taxi cabs. That's yellow cabs, but there's more. And they transport over approximately 500,000 passengers every day. So this was 2016 data. And this value is more than 600,000 or even 700,000 in 2013 when Uber was not there. So what really happens during these years is the rise of these app-based services, or what we call mobility service providers. They enter the market. They're Uber, they're Didi, they're Lyft, they're Halo, and they're rising their market share. You can see like this is how their market share is increasing. And right now in 2017, we collect New York City data from Uber, and we found that the demand is almost on par with yellow taxis. So actually it's quite significant. So why I'm talking about these two, it's because the market has been changed. So what has been changed? There are several things. The first thing is the market rule has been changed. It's changed from a monopolistic market to a competitive market. That's one thing. And there's no entry regulation anymore. So whoever can join the app-based services become a driver. So basically there's no cap on the number of drivers you can have. And the habits of we're getting a ride is also changed. Most of us will no longer do street hailing, so we're just using apps to order a ride. And what more interesting and what really matters in this study is we are now having a growing interest in real-time operations. So if you're familiar with taxi literature, you have found most of previous studies are doing what? Doing entry regulations, doing pricing structures. That is from a very aggregated model using Markov-scopic, like using some theories from economy. But right now, we're focusing more on real-time efficiency. We're doing ride matching, we're doing recommendation, we're doing search pricing. Because of what? Because we have data. So issue still remains. What issue is there is these things are not effective. It's because we're doing it in a reactive way. We wait until demand shows and we pair with each other. We're doing this. That still is inefficient. And what's the most effective or most efficient solution is we do it in a proactive way. So we predict the demand and we take action before the demand emerges. So that comes to the key input for these kind of things is we should have a very accurate understanding of the future demand, like in the near future. And this motivates our study. So the problem studying this research is kind of, to visualize it is kind of easy. It's a very simple example. So assuming we have a city divided into several zones, in this case 5, what we're going to do is we know the demand in the past, maybe these steps, and I want to predict for the next time step or maybe next few time step. So what we're doing is we're learning from history data, right? So we have these and we have the output, we learn from them, and then we predict. We're not doing point estimation, we predict the distribution. So we want to know what is the distribution of demand in each of these areas in the next few time steps. So to summarize this one, it's like the input of this model is the length of time interval, you name it, 10 minutes, 5 minutes, 15 minutes. And we divide the study into several zones. And we have the historical data, we learn from it. And then the observed demand in the past few time steps, use the input and use our model and predict what we have. It's a demand distribution across the study over the next k time steps. The demand distribution is really helpful. So we know the kind of uncertainties and stochastics that may emerge to help better do the optimization. So Given all these, but if you try to do Google search, doing Google Scholar, search for like taxi demand prediction, you'll find there's very few studies that have actually doing this work. So why is that? It's because of there are several challenges. So the first thing is noisy data. Let's make a very simple comparison. So the figure on the left is what is the aggregate taxi demand, like daily taxi ridership across the whole New York City. You will find there's a very clear pattern, day-to-day, repeatable, easy to predict. But what happens if you zoom in like a zone in lower Manhattan, middle Manhattan, and upper Manhattan, in every 15 minutes, you observe the demand is very, very noisy and non-stationary. It actually increases the difficulties in predicting this kind of data. And more than that, it's like, okay, we all know spatial and temporal correlation exists for this kind of ridership. Then if you look into different days, we see that, okay, nearby areas actually are highly correlated, but not for the far areas. Same thing for the temporal correlation. For the same place, the demand within the consecutive time steps are highly correlated, and this correlation decreases across the time. But the trickiest part is these autocorrelation or correlation are heterogeneous, meaning that at different locations, we have different correlations. So how are we going to model this to help better predict the taxi demand? That's the question. And more importantly, the data availability. We're in the era of big data. We're talking about deep learning models, which requires significant amount of input data, a lot of features, and training this. But I would argue here that actually taxi demand data, maybe it's only a small data, not a big data. It's because of this. Short-term taxi demand is highly sensitive. First of things, in an urban area, the land use changes dramatically. When we observe the same location, it was a restaurant a week ago, but it becomes a market, supermarket the next week. Obviously, the demand will change accordingly, and it'll be very, very different. And there's more that comes to play. There's time of day of week, day of year, which is a holiday. And seasonality also comes into play. And more important is change of market structure. A typical example is taxi ridership. We can't use the data in 2013 as a training sample to learn and to predict taxi demand in 2017. Because Uber was not there, the ride-sharing apps are not there. Similar applies here. And if you think one day of data as a one sample, so same time tick, there's only one time tick per day. So 1 day of data is one sample. And data a long time ago into history may have very little value in predicting current demand over a short time. This gives rise to the issue of we have very small size of training data, and how are we going to do this? So with this challenge in mind, so we have the methodology presented here. So we have the input is X, which is kind of a column, a transpose of column vectors for each location, same demand distribution, and over the past history. And then we have the output is a predicted demand each individual locations, which is what we are modeling is we're modeling the probability density function. So we're modeling the demand at Y given what? Given all historical observations and also the demand, the prediction for all other areas, meaning that it's a structured output. And we have an assumption here is short-term taxi demand. Each region follows a Gaussian distribution. Well, it is typically true for most of the areas. It might not be true for some, but it's not a problem because we can apply like Copley transformation to transform any marginal distribution to Gaussian and then do the prediction and convert it back. So with that, we present a Gaussian conditional random field model, which takes the probability density function as this one with the constant term, and we can predict the parameters using the maximum likelihood. It's quite straightforward. So to understand the model better, it's like that's the density function. Here's the underlying graph model. So what is that? It's like all of these are history observations. These are future predictions. Then future predictions are correlated. We do maybe they're correlated with all of these historical demand, but also future observations are correlated among themselves. So what we're going to do is we're going to use the model to predict the correlation on each edge. So this edge contains information of temporal correlations, spatial correlations, and whatever correlations are there. So the model determines all we learn from data. So why using GCRF? Why not other models? So first thing, spatial temporal correlation. The second thing is it's a discriminant model rather than a generative model. So meaning that it will have a small error bound, and there's no need to model the full distribution, which is P, Y, X. So it's less a hassle. And because of the complex spatial temporal distribution, what happens is that we are very likely to have a very dense covariance matrix. Everyone may be correlated with the other, and it will be intractable to compute for large area over a long time period. So For the conditional random field model, it's like we only want to infer the inverse of a correct model because of conditional independency. And therefore, this matrix is likely to be sparse rather than dense. So it kind of reduces the complexity of computing these things. It'll be really, really fast. So there's two more challenges remaining with this model. The first thing is overfitting. So if you denote the input of x as n, the length of y as p, the number of parameters to estimate is this one. So the model we're overfitting if training data size is small, it's because the feature is large, the training size is small, it'll overfit. Given an example is like, if you want to predict demand for 30 zones using 2 days of history observations, so the input size is what? Each step is 15 minutes. We'll have the feature is like 5,760 features. If you want to match the size, like match the training size with the number of features, we're going to use 15 years of data as input, but it's not worth that. So how we're going to do this is obvious. We don't have more data, then we regularize this model. So we penalize the two dependency matrix with L1 regularization to make it as sparse as possible. So we lose mathematical properties because it's no longer differentiable. Well, traditional numerical approach won't work well because of the size of the problem. And for this problem, to address this issue, we apply the second-order active set method, which was proposed by Whiteoak and Coder from CMU back in 2013. Okay, so the last challenge right here is accuracy. So for the accuracy in this paper, it's not only for the mean, but we are care about the distribution. So the covariance is another thing. And we say short-term taxi demand pattern vary very significantly over days, right? And we have a sparse GCRF. It's regularized, so kind of from a strong learner leaning towards a weak learner. It's a more simple model. And single machine may not learn the data best. So what we can do, we do boosting. It's an obvious choice. And it may improve the mean, of course, but it will worsen the covariance. Why that is because what that boosting does is does a weighted combination of several machines, right? From learning and penalizing all this data. And the combination of several multivariate Gaussian from each machine is what? It's a Gaussian mixture model. For Gaussian mixture model, the mean is a weighted mean, but the covariance is the weighted covariance plus the dispersion term, which kinds of characterize the dispersion from the mean. So if you have a lot of machines combining together, this mean may be very accurate, but the covariance looks like what? Like a uniform distribution, which makes no sense at all. So we propose our final model, which is called a boosting-GCRF. So we're using a product rule rather than the weighted combination rule. So here is like this product rule will improve the mean estimation, but at the same time, machine with higher variance, meaning that they're less certain with the prediction, will receive less importance in the final combination of. And the resulting covariance is no worse than the machine of the least predicting uncertainty. So it's kind of bounded the covariance to make it not like too conservative. And you can find the detailed algorithm in our paper. So here we go through the results. We use 2015 New York City taxi data, or 2016 data is out there, but the study was conducted in 2016, so we use 2015. And study area shows on the right, where I choose to use Manhattan, because like 95% of trips are within Manhattan. There are very few trips out there. It doesn't make sense to do that. So a year data, 365 samples. We divide into 48 regions. Each time step is 15 minutes. We divide the data into 75% of training, 25% of the standalone testing set. We don't touch them until we train the model. For the features, we scale the demand into the -1 to +1. And we further generate a Gaussian radial function for each of this demand to quantify how they deviate from the average case. So it's like counts for like anomaly conditions. And we choose several benchmark algorithms here. The first is like, now we have boosting. What about testing for bagging? So the first is bagging GCRF. And we also test with the feed-forward neural network. We optimize the structure. Finally, we find like single layer with 10 neurons and regularized model fits the data quite well. And we also try the boosting regression tree and gradient boost tree out there. And here's the results. So first is the training arrow. So we do all this on the training data only, so that's 75% of the data. We do 5 cross-validation. We use RMSE as a metric. We create 14 scenarios, which is like we use 20 steps of data back into history, which is like what, 5 hours into the past, and want to predict 2 cases. One is an hour of demand ahead of future, and 2 hours of demand ahead of future. And we test for seven different times of day, like starting from 7 a.m., 9 a.m., and 1 p.m., all these things. So it covers morning peak, off peak, and evening peak hours. Okay, so it gives 14 scenarios. And here we just present the average performance across all these 14 scenarios. For each scenario, there's 5-fold cross-validation. And we found boosting GCRF being the best in 13 out of 14 cases, whereas the rest cases, the base GCRF model is better, which is a morning peak because it's the hardest case. We're using 2 a.m. of data to 7 a.m. and predict 7 a.m. to 8 a.m. And we found the boosting GCRF have smaller RMSE and also have very lower standard deviation, means the prediction result is stable. And we have best during the best performance is during off-peak hours, and we find the worst performance during morning peak hours. But in overall, there's like 4.13% of improvement over the baseline GCRF, which suggests like the boosting is quite effective. Moreover, the biggest improvement observed during off-peak hours is 7.42. And actually, the improvement over standard deviations is more, I would say, more significant. So stableness of the model is quite good. Okay, talking about training, then we're going to prediction. So we use all the training data, train the model, and then we test on the standalone testing set. So here's what happens. Same 14 scenarios. Now we use matrix, both RMSE and MMAPE. So the modified MAPE is for what? So some tracks has 0 observations. We need to account for that. So that's why it's a modified one. And the average improvement across all the scenarios is 4.9%. It's almost 5% in terms of MAPE. And the biggest improvement we found is almost 13%, which is for case 4. It's like an off-peak hour prediction case. It works very, very well from medium to high demand area. So like these two graphs. So the blue line is the boosting performance, and the red line is the baseline GCRF model. We can find the MAPE for these areas actually consistently below 5% for those high demand areas. But for the in some cases, for the low demand area, the MAPE is quite high. You can understand that because 3 versus 5, only 2 is the arrow, that is a mean absolute arrow, but the percentage is quite high. Okay, and this is the average MAPE, so it's 12.4% over all the scenarios, and the best case is 10.2. Okay, these are the regular cases, but what about anomalies? We have snows, we have large events where the demand surge, demand pattern changes. So we check if the model is robust to anomalies. We construct a test set which contains what? It contains the top 10% of the samples which deviate most from the average case. And we use this as testing set, and the rest, the previous one, and we use still the same model from the 75% of training data. And we test boosting algorithm performance versus others. What we find that, okay, it's like boosting GCRF and the ANN model have the best overall shape, meaning that they are clustered around the red line, which is 100% correct. And you will find that the baseline GCRF and bagging GCRF are all overestimating the actual demand because they're leaning like upwards toward the line. But ANN, you find that the shape looks good, but there's a lot of outliers, okay? And the MAPE for the boosting GCRF for the anomaly case is 12.4%. Compared with the base model, it's like 18.2. So the improvement is much more. Okay, so these are all mean comparisons. So what about the distribution? So we're talking about the covariance. So we want the distribution to be what? To be as close to the real case as possible. Like, if we found 19%, exactly 90% of real samples fall into 90% of confidence interval, it will be great. So we construct confidence regions of estimations around the mean, but it's kind of tricky to construct confidence regions for these kind of Gaussian mixture model. What we can do is for each dimension, construct them and do a Cartesian product, but this will overestimate the actual one. So we apply the Bufferoni correction to that one to correct the overconfidence issue. And then we present the results here, which is corresponding to morning peak, off peak, and evening peak for the 68 confidence level, 90%, 95%. So what we find here is what? Is GCRF, like bagging GCRF, they all make very, very conservative prediction. Like actually 68 confidence interval covers almost 98, 99% of the actual data set. But for the boosting GCRF with the product rule, we find that it's like, except for the morning peak, which is a hard case, for other cases, it's quite close to the actual confidence region. So it's kind of, we can conclude that it gives a very tight confidence region to the actual data, which is quite good. So here's the conclusion. In this study, we discussed the properties of short-term taxi demand. We proposed a boosting GCRF algorithm, and we compared the results with some benchmark algorithms. So we found that first, the model delivers accurate estimation in terms of mean. And the performance is stable across different cross-validation studies. And the model is robust, kind of robust to anomalies. The model is able to capture the true distribution. So in future works, we'll put more efforts actually on other features. Right now, we're using very limited anomalous features, which is the time like a time series kind of demand. But we can combine other information like weather, the ridership from other modes, and then use all these things together to kind of improve the prediction accuracy. And also we want to investigate the performance of this model on other tasks because there's like transferable. Like we can predict using this similar model to predict the link flow, to predict the travel speed, etc. That concludes the presentation. Thank you.